Okay, number 3 for area of a region between two curves. So we're looking at more complex situations that require a bit of initiative and insight. So not straightforward, but not impossible. So we've got a region that is bordered by y equals root x, y equals 6 minus x, and y equals 1. Let's find the area of that. Let's have a look at a drawing first. With the aid of technology, you can see we have root x in blue, 6 minus x in green, and in purple, y equals 1. Note in particular the graph of y equals root x, and it stops at 0, 0. Okay, because it is not possible to have any values there beyond that for a couple of reasons. We can't, in the real number system, take the square root of a negative, so x will not go left of 0 on the x-axis, and it will also stay above the x-axis. I should say it shouldn't go left of the y-axis, and it will not go below the x-axis because the value of the square root of x is always positive. This is because we're always taking the square root of a positive number. It is not possible to take the square root of a negative number in the real number system. So don't get confused when we're solving equations sometimes, because that will have a plus or minus outside of the square root, like so, and you need to add that. Now that's not what we have. By the way, the negative graph would look like the following here. So you would need to place a negative on the front, which is not what we have. Okay, we do not have that. Alright, so let's switch these back on and have a look at some analytical procedures now to get the show going. Put little subscripts below each of the y's symbols there. So equation 1, 2, and 3. And for y1, that's root x. So x is part of the set where we have from 0 through to infinity. Okay, so and we have y also from 0 through to infinity accordingly. Okay, a few other things that are important to establish first. This will have an x-intercept at x equals 6, okay, because when we solve that simple equation there, 6 minus x, we get x equals 6. So that'll be the intercept, which we'll need. So for the points of intersection of y1 and y2, we have root x equals 6 minus x. We can square both sides then. So we've got x equals 6 minus x all squared. Expanding, we get the following, and grouping it all together so that we can solve it, because we're going to set the side equal to 0. We've got minus 13x plus 36. It factorizes as such, and so we have apparently we have two solutions. So x equals 4, and that will give us the point of intersection 4, 2. Now we saw in the diagram in the graph before the following here. Okay, and technology does verify that our point of intersection right there on the top of this region, see, the region is actually where I'll just make it a bit clearer. So it's in here. Okay, it's not a great colouring in pen. I probably could have selected a thicker pen to do this, but you can see it's like a triangular, almost like a triangular area. Of course, the blue line's not straight line. Vaguely triangular, but not really. So that's the region. So you're thinking, okay, we've been dealing with the green and the blue lines. They only look like they're going to intersect once because that green line's not coming back. It's a linear function. So what's the story? because it looks like we've got another solution, 9. When we use the null factor law here. Well, x does not equal 9. And it's fairly apparent that I'm using a new tablet, drawing tablet, so I'm a little bit clumsy in this video. Forgive me in advance for any more stuff ups I might make. So I'm getting used to it. But it's not equal to 9. It is equal to 4, but not 9. You could quickly show graphically why that is the case. You would need this one here to intersect with the linear function. So eventually it does intersect that one. Alright, so but it won't intersect this branch here. And remember, the black branch is not actually part of consideration. So there is no second line of intersection there. If we tried to sub it in, we get 6 minus 9, negative 3. And for the root x function, we have no negative y values as we've established. So we would need that other branch, which is not part of the function, so we can't include it. So there's only one point of intersection here. And that's one of the more insightful aspects of this question. Putting in a couple more points of intersection, the last two in fact is quite easy work. You can see them there, and you can see that's verified with the technology. So we have 1, 1 and 5, 1. So we've got our 3 points of intersection. Okay, now to set up the integration to get the required area. So we need to consider one of the methods or one of the variations we've looked at in previous videos. I'm going to have a quick look at the graph too. In the interval from 1, 1 up to 4, 2, so from 1 to 4, the x values, we can see that the area is bounded by the root x function and y equals 1. So it'll integrate from there to there, and then there'll be a second part to that where the green line, 6 minus x, is the upper limit. So we need to integrate accordingly. Okay, so we can see that we've got the first part there, the difference of the two functions, using methods we've looked at previously, and then the second part there was from 4 to 5, and it's the difference of the corresponding functions there, which is 6 minus x. Y equals 6 minus x and y equals 1. We go through and integrate and evaluate, and we get that next line. Okay, step of integrating, and then we've got to apply the limits of integration on the next few lines and evaluate, and that's 16 right on the right hand side at the end, and evaluating that we get 13 on 6, or 2 and a sixth units squared as the required area. The second of two examples is the following: the area bounded by arc sine x, x equals a half and y equals 0. Okay, just getting a sketch done with the aid of technology there, and we can see that we have an area, and let me just see if I can point you into the right direction there. So that's the area there. Again, it's a little bit triangular, but the arc sine x graph is not straight, so it's not a triangle. We've got three key points there, and so we need to verify. Well, that's verified, but we need to actually do that analytically. But before we do that, I want to look at the first function here, y equals arc sine x, and tap into some of the stuff we've done previously. And so if we rewrite that in a different form, we could say we have sine y equals x, and x has a restricted domain. That's from a previous body of work we've done, and it's restricted between -1 and 1, and thus the range is restricted accordingly to -pi on 2, pi on 2. Okay, so that's some previous work you need to go back to if you can't remember or understand that part. So we have, if we want to consider the integral, whoops, there's my new stylus. So for the integral of something in that form, we'd actually have the integral of sine y dy. Now that would be like if we had x and y axes as normal, but if we have some function, and if we're integrating that over certain limits, we'll find the area under the curve like so between the y-axis and the curve. Okay, so if you didn't know that, it works essentially like that. We can actually use that property if we like in a complementary way, and I'm going to show you that soon. So for the first two equations, if we set them equal to each other, so because they're both x equals type equations, so a half actually equals sine y. Alright, so we're making these two equal for points of intersection. Remembering the restriction on y there, negative pi on 2 to pi on 2. So y will equal pi on 6, not 5 pi on 6, because of the restriction on y. We get a point of intersection of a half, because we already know it's x equals a half equation, and that pi on 6 for y. So there's one of our points of intersection. And we'll look now at the intersection of the first and the third equation. So y equals 0 and y equals inverse sine x. Now since sine of 0 is 0, if we set those two equations together, we get x equals 0. So we have the point of intersection 0, 0. Now what we're going to do is we're going to integrate such that we find this area here, as I said before, and we're going to subtract it from this greater area, which is a rectangle. That whole area in there, and we'll be left with what I'm going to put in yellow, like so. And the yellow area is the one we want, as you can see. So that's what I meant before by complementary way. It's the complement of the area. So we have a rectangle minus the complement gives us the area we're requiring. So to give us the black area we just saw on the graph, we integrate the sine y dy between 0 and pi on 6. To give us the rectangle that I referred to in red, we have to go pi on 6 times a half. So have another look at the diagram, scroll back if you need to. So we subtract we go rectangle, subtract the integral of sine y dy in those limits, and we get pi on 12 minus negative cos y in the limits described from 0 to pi on 6. And that will give us pi on 12 plus the second part. When you take the integral and sub it in, you'll get root 3 on 2 minus 1. So that's the exact value, and I'm not going to worry about decimal approximation. So we got pi on 12 plus root 3 on 2 minus 1.